Chapter 7.8. You've made it through Chapter 7, all about factoring polynomials. This is a major concept in algebra and beyond, and you'll continue to work on it next year and the years to come. So in our final chapter here, we're going to look at factoring by grouping. And when we factor by grouping, this involves factoring a polynomial with 4 terms by grouping the terms into pairs. Then, using the greatest common factor, the GCF, on those pairs to create your binomial factors. That will make more sense when we do our few examples here. Finally, a polynomial is fully factored when it is written as a product of unfactorable polynomials with integer coefficients. All right, so let's take a look at factoring by grouping. You can always refer back up here to our key concepts should you need a reminder. All right, in example 1, we want to factor each polynomial by grouping. So I take a look, I see that I have 4-term polynomial, x cubed plus 3x squared plus 2x plus 6. When I group these, I'm going to group the 2 highest degree terms and then the 2 lowest degree terms. So I'm going to first ignore this second grouping, and I'm going to just look at the x cubed plus 3x squared and factor out the GCF. Well, the GCF of x cubed and 3x squared is simply x squared. When I factor that out, I'm left with x plus 3. And my next 2 terms, I am again going to kind of ignore this first term here and look at the GCF of 2x plus 6. Well, the GCF between 2x and 6 is positive 2. When I factor out a positive 2, I'm left with x plus 3. Whenever we factor by grouping, we'll have kind of this little phenomenon that in the parentheses here, my remaining factor will be the same once I factor out the GCF of the 2 groupings. All right, so this actually tells me what my 2 factors are. It is the x squared plus 2 and the remaining factor that I have in the parentheses that is common, that I have highlighted here, which is x plus 3. But you only need to list it once. So my factor by grouping gives me, or results in, x squared plus 2 times x plus 3. All right, let's try the next one, example 1b. I have 3p to the third minus 5p squared plus 18p minus 30. Once again, I'm going to group the 2 highest degree terms and the 2 lowest degree terms. Factoring out a GCF, the greatest common factor, of 3p cubed minus 5p squared, I'll pull out a p squared. I'm left with 3p minus 5. Next up, as I look at 18p minus 30 and ask what divides evenly into both of those terms, I can divide out a 6. Positive 6, and when I divide out a positive 6, I'm once again left with 3p minus 5. So you can see inside the parentheses there that 3p minus 5 is common to both of those GCFs, which means my final factors are p squared plus 6 times 3p minus 5. And that is my final factorization. Notice that I can't factor any further this p squared plus 6. There is no pattern. I cannot factor the sum of perfect squares, nor could I factor the x squared plus 2. So these are both fully factored. All right, example 2 here in our final factoring examples of this chapter. We are going to factor completely. And when we factor completely, we're going to go through this little list here. To factor completely, we're always going to first start by checking for a greatest common factor. If a greatest common factor exists, we'll factor that out first. Then we're going to look for any patterns, such as the difference of perfect squares. This comes, remember, when there's just 2 terms. Otherwise, if there are 3 terms, we are going to use the factoring techniques that we learned in this chapter. And if there are 4 terms, we'll factor by grouping, just like we did. All right, here we go. We're going to take a look here at example 2a. We have 3x cubed plus 12x squared minus 15x. I see that all 3 of these terms are divisible by 3x. That's my greatest common factor, and I'm going to factor that out first. When I do that, I'm left with x squared plus 4x minus 5. Now, I should ask myself, can I factor this trinomial further? This is a trinomial with a leading coefficient equal to 1. I would be looking for factors of negative 5 that would combine to give me positive 4. And that exists. I have a negative 1 and a positive 5. Those would be two numbers that would multiply to give me negative 5 and combine to give me 4. So I can factor this polynomial further into x minus 1 and x plus 5. My final and fully factored form of this polynomial then would be 3x times x minus 1 times x plus 5. All right, in example 2b, I have two terms with a minus sign between them. Now, the tricky thing is that these are not perfect squares. So this is not going to fit my pattern of difference of perfect squares. However, I got to first look to see if there's a greatest common factor. And in fact, there is. I can divide out a 7x squared from both of these terms. So let's divide out a 7x squared, and when I do that, I will be left with x squared minus 4. All right, again, ask yourself, can you factor this further? Here now we do have the difference of perfect squares. Two perfect squares with a minus sign between them, which can factor down into the conjugates x minus 2 times x plus 2. Since I can't factor 7x squared down any further, I'm done. This is fully factored, and the three factors that I can break that down into are 7x squared times x minus 2 times x plus 2. Great job on sticking with factoring in Chapter 7. We'll get lots more practice in class. See you then.